lines that go through the surface, okay? So this is, and what is E right here? Yes? So can you now look at this expression? We are doing cosine, we're doing magnitude of E, magnitude of A, of dA, cosine of the angle in between, yes? What is the angle between these two? No, look again, 0. E and dA are in the same direction, yeah? What is the angle between these two?
0.
0. The angle between the top faces and E?
90.
90. So which of these terms should vanish? These last two terms should vanish. You agree with me? Because the electric field is outwards and perpendicular to the sheet, what are we going to say? It remains constant over the little dA chunk that we're taking for both cases. So what would the integral of E dA be? Remember how we do this? Magnitude of E, the definition of the dot product, yes? Magnitude of E, magnitude of dA, cosine of the angle between. So once you do that, you're going to get nothing but this. Do you agree? Because the integral of the dA is simply the area of this square that's on the side. Yes? Each square has an area of a square. So you're going to get EA squared, you sum it up, you get 2EA squared. Yes?
So just to make sure, you said it's squared. So we're choosing like not a rectangle or like what?
We're using a rectangle.
So okay, so it's not.
So this length of the rectangle is X.
Okay.
And the other ones, the other two are A and A.
Okay, I got you.
See what I mean? Why? Because this is the easiest Gaussian surface to enclose this system in, such that it comes out simple and straightforward.
Okay.
So now that we have the flux, what do? If we have the flux, we multiply the flux by epsilon naught, and that should equal the charging flow. Do you agree with me? I would like an expression for the electric field that contains the variable x. Why? Because I will plot different values of x, where x, please pay attention, is going to be different values, but always inside the slab. Yes? So, can you tell me how out of this expression can I grab an x? It has to be with the term that has Q enclosed. Q enclosed is what's critical here. We are inside the slab. So can we simply say that the charge enclosed is the total charge of the slab? It can't. It has to depend on x. How does it depend on x? What do we know? Look at this. The volume charge density equals Q enclosed over the volume. Do we know what the volume of a cylinder is?
You mean a yeah, a rectangle?
Not a cylinder, the slab,
yeah.
the square. Not the square, the rectangle that encloses the thing. What is the volume for the rectangle? Length times width times height. Tell me that in terms of A and in terms of X. So this is length, there's height, and there's width, right? So height and width, that is A times A. Yes?
Right.
So that is A squared. And what is length? If you look at that being X, what is length? 2X. Do you agree with me? So that is volume. Notice that I cannot say that this is D. Why can I not say that this is D? Right, so what would I have to ask you for you to use D? Your Gaussian surface would have to be what? Completely enclosing the slab, which is actually called D officially. So to understand this problem, please don't take it just from my slides. Sit down and work this out, make sense of this Gaussian surface, of the symmetry of this problem, and produce this answer yourself. So then x, various x's to plot, all of the x's between smaller than d. Part D of this problem asks you to then find the electric field way outside D, at a point far away from D. And so it is exactly the same, except one thing changes. Right here, the Q enclosed will not be in terms of x. There would be a D in this expression. Okay? So this is a nice problem. It teaches a lot how to what the recipe is for these kinds of problems. So planar symmetry. Let's look at cylindrical symmetry. Let's look at a charged wire. So imagine charge distributed evenly on a very long straight wire. And the Gaussian surface that makes sense here to enclose this is in a cylinder. Just because it's beautiful, it's simple. Tell me immediately what does the geometry tell you? The electric field has to be perpendicular to the sides of the cylinder, yes? What would be the flux through the top face and the flux through the bottom face of the cylinder?
Zero.
Zero. So you can already see it. It's a beautiful surface to enclose it in. So again, this is the height of the cylinder. This is 2 pi r, of course, as you know. And let's just then figure it out. The electric field points radially outwards in this case, but I could give you on the test a negative charge, right? Negative line of charge, which simply means it puts, what does it mean? Yes, thank you. So, consider that, and this is what you have. You have the flux. The flux is the very first thing we calculate. Of course, now we know that the flux in both of the ends is 0. And for the sides of the cylinder, it's simply going to be EVA. Why? The E is constant. We bring it outside the integral, and right, the dA will be the area element of the side. Yes, the surface area that's piercing, the electric was piercing through. So then let's do it. What is the surface area for the cylinder? Fairly straightforward. The E comes out of the integral. The integral of dA is nothing other than 2 pi RH. Yes, for a cylinder. So now look the pretty beautiful thing you got going on here. So you've got epsilon naught times E times the surface area of the cylinder equals the charge enclosed. Yes? How do I write the charge enclosed in terms of lambda? Again, what is charge enclosed here? It's a line of charge. So now, instead of being rho, it's what?
Okay.
What is lambda? Q enclosed per unit length. Yes? How do we write length in this case? Well, the length that my Gaussian surface is enclosing the rod, right? Which is h, the height of my cylinder in this case. So put all this stuff together, solve for the electric field in terms of lambda, and this is the expression that you get. Lambda over 2 pi epsilon naught times little r. Can you tell me what little r in this expression is? The radius of flux. Yes, so problems from this cylindrical symmetry will be concerned highly with R. What are you going to have? You will have concentric shells, concentric spheres, and the question would be either find the charge enclosed or the electric field at different R's from the origin. Okay? Yes?
Is the reason why you don't care about the wire outside the cylinder just because it doesn't contribute to the actual...
It doesn't contribute to the actual flux because look what happens. This is the top face of the cylinder. This is the bottom face of the cylinder. The electric field comes out radially. I'm trying to do this in 3 dimensions, if you know what I mean. It comes out like a sun. So this face, the electric field skims the top of the face. It doesn't come through the top of the face, right? So this is dA, this is E, and this in 3 dimensions is 90 degrees. Do you see what I mean? So it does not pierce the top cannot penetrate the surface. So in this case, this term is non-existent. What is the integral of E dot dA? All right, magnitude of E, magnitude of dA, cosine of the angle between E and dA. In this case, E is out, dA is out. What is the cosine of that angle?
0.
Cosine of 0 is 1. So this is what you have. The E comes out of the integral, right? Constant, uniform. And I'm integrating over dA. What is dA in this case? The surface area of what? Of the cylinder, which is also 2 pi r times L. Do you agree with me? So I've got the flux. I've got the flux. Are you still with me?
Yeah.
I got the flux. This is extremely exciting to talk about, I know. So I got the flux. And now what do? I multiply by epsilon naught to get the total charge enclosed, and this is Gauss's law. Agree with me? And again, what am I trying to do here? I'm trying to find the electric field. Yes? But I would like this electric field to be a function of R. Yes? So this is why I need to have this little r right there where it's at. So I got Q enclosed, epsilon naught times phi. I'm almost ready. Am I ready? Let's see how ready I am. I'm here. Yes? Let's solve for the electric field right away. Boom. Done. That's the electric field. So I've got E, Q enclosed, L, and R. How many things of these things you know? You know L. Yes? You can figure out R. Yes?
Right.
And what else do we need to figure it out? Q enclosed. Now listen, is Q enclosed going to be different for different little r's? Yes or no?
No.
No.
Yes.
Oh,
Look
man.
at it. If I'm out here, my Q enclosed is Q1 plus Q2. Do you agree with me? But if I am in between the two shells, what is the only charge enclosed? Q1. Do you agree with me? So it makes a difference. Okay? So in this case, we take the radius of our Gaussian cylinder to be, they tell us that they want us to find it at 2R2. Well, 2R2 is given in terms of R1. Eventually, when you plug in the numbers, you get this. 2.6 times 10 to the negative 2. We have little r. We're almost done, except we need to find the charge enclosed in the cylinder. So the charge enclosed in the cylinder, because we are all the way out here, outside, will be Q1 plus Q2, okay? Q2 in this problem, for some crazy reason, is given in terms of Q1. So plug in what it is, eventually you'll figure it out, is the negative Q1. So now you are indeed ready to plug everything, and this is what you get. Typical difficulty of this data of an exam. I believe if you sit down and you work this out, making sense of it, you'll be able to understand fairly straightforward how to do this. The things you have to take care of first is, you want to find, just like the example with the slab, you want to find the electric field in terms of X for the slab, in terms of R for this one. And depending on where I'm asking you to place your Gaussian surface, then you take care of the little r and the charge enclosed. So this all has the same recipe. It's just a matter of sitting down and working them out one by one. Easiest and prettiest of all is the spherical symmetry. How are we going to get to the spherical symmetry? And in fact, we'll get to Coulomb's law so easy, so beautiful, so elegant, just using Gauss's law. So imagine a point charge, yes? This is the electric field, the magnitude of the electric field for a point charge, yes? So radially outwards. Look what happens. Take a positive charge and surround it with a neutral conducting shell. Okay? So what happens to the positive charge?
Still radiates out.
Still radiates outward, right? Because it's a neutral conducting shell. But what happens to the conducting shell?
It
The
gets
conducting shell, the charge is rearranged within the conducting shell, right? Shell. So look what happens. There can be no net electric field inside the conductor. You know that, right? So that means they rearrange themselves in such a fashion as to cancel out, right? Positive, negative, okay? So the field outside, by the way, what would be the field outside, very far away? should be no electric field. So, again, Gaussian surface here, no electric field whatsoever. Plus and plus and negative cancels out. Yes? Electric field here, same thing. Yes. Good. So what if there are charges fields outside? Does it matter? It does not. Why doesn't it matter? If I do my Gaussian surface here and there's an electric field outside, what does it affect it? Do the electric field line go through? Yes, but as they go through, they do what else? Come out on the other side. So still doesn't affect it. No net charge enclosed, no electric field inside. So the field inside a conductor is zero. Yes? But the conductor has no effect on the field outside the conductor. Does that make sense? The only purpose of the conductor, like we talked about last class, is to provide a pathway for the charges to accommodate. This is what's called a Faraday cage. Have you heard of Faraday cages? Yes, pretty much your car, as long as it's not a convertible, is a Faraday cage, which means outside is conducting material, inside the conductor, there can be no electricity. So if you're ever in a store, there's lots of lighting going on, get in your car. Right, you've seen this picture.
I've never
Right?
seen that.
So automobile, airplane, passenger compartments are all Faraday cages. They protect the passengers from electric charges such as lighting. What else? Elevators, dead spots. Those are Faraday cages. Okay, they're metallic conducting frames and balls that simulate the cage effects. Okay, nothing comes inside the conductor, not even the waves you need to speak on the phone. Okay, so it's all shielded from the outside. The scan room of an MRI machine has to be a Faraday cage because you do not want anything external to contribute to the reading that you're getting from the machine. What else? Microwave. You stand in front of a microwave, what do you see on the door? It's a meshy looking thing, right? Well, that meshy looking thing is also a Faraday cage. It contains the electromagnetic energy and it shields it from the exterior. Okay, so that's what you can just stare at and see giving up. The dipole molecules, remember? So that's why when you speak on the phone, you need, what do you need? You need an antenna. What do you need an antenna for?
Carry waves.
To receive.
Okay.
But you do not need an antenna to transmit, right? So you have some sort of a Faraday cage that to receive needs an antenna to tune in, but it's giving off constantly, right? That's what they say it causes cancer and all that kind of stuff. I don't know. Anybody recognize that?
Is that Better Call Saul?
No. Better Call Saul is the, what do you say?
That's Better Call Saul.
It's the speed up of this one.
No, no, that. Okay.
Oh, no, it's not. You're
Yeah,
right.
there you go.
It is
Okay.
Better Call Saul.
All right.
Right. Now, a Faraday cage. Anybody seen this show? Anybody else has seen this show? That's it? It's
I
it's
think I
a
want.
spin-off of Breaking Bad. It's just about the lawyer.
Yeah.
And this is the brother of the lawyer who used to be the head of the firm, and he's just completely crazy about electromagnetic fields and all these kinds of things. So he's got one of these. Have you seen these? Have you ever gotten one of these? Like if you run races, like really really cold, or like the paramedics have it, like they're supposed to keep you up really fast. Space plane. How cool is that, right? Okay, so let's talk about the shell. Let's talk about the shell. Really? Are you going to keep going? Yes. I have a shell. Instead of a charge, now I have a shell. But look at this. Look how beautiful. Did I tell you about my quantum mechanics professor? I had an advanced quantum mechanics class. I don't even know why I took the class. I didn't need it. And it's horrible. But the guy was really, really cool. And he was from Armenia. And he has this very thick accent. And he used to, it was a There was no time to erase, so he wrote everything here. And then when he was gonna say something really, really important, he was like, looky here, looky here. Very important. So I always think of him when I say look here. So instead of a charge, we're gonna have a thin spherical shell. Because we like it. We like shells. I want you to think of a shell as something cool that you're going to enclose in a sphere. Okay, a shell is something that you enclose in a Gaussian sphere, like a G-sphere, right? So this is my shell, and look at the R's. R's are going to play a big deal here, just like in the cylinder. Your homework problems and your exam problems. One of these things is going to be on the test because it's pretty, so it is going to be on the test. So look, R, little r, capital R, S1, S2, and this is charge Q within my thin spherical shell, yes? So you're going to find many things, either the electric field here, outside, or maybe the electric field here, inside, right? Or maybe the electric field far away. By the way, what should be the electric field at a very, very, very large distance away from a uniformly charged spherical shell? No. The same as that emitted by a point charge. Why? Because you're so far away that the shell looks like a simple point charge to you. So, exactly. So we should be able to get that result from here. So, yes. What if it's not a point charge, but a thin uniformly spherical shell of some radius capital R? Same argument applies for R much greater than R. So this little r right here, greater than R. The integral of E dot dA is simply E dA. Remember, this is a sphere, so this is the Gaussian surface, it's a sphere. The field is out if it's positive, comes in if it's negative. It's symmetric, it's uniform, and it is piercing that surface perpendicular. So this integral is E dA, where dA in this case is the surface area for a sphere, yes? What is the surface area for a sphere, my beautiful people? Unlike it. So theorem 1, any spherically symmetric charge distribution acts on particles outside the shell, we talked about this just now, as a point charge at the center of the shell. That's theorem number 1. We will prove this with Gauss's law, and it's going to be beautiful. Theorem 2, any spherically symmetric charge distribution exerts absolutely no force on a particle inside the shell. What does that mean? The electric field inside the shell has to be 0. We've talked about that, we've seen that before. So how do we get these theorems? What do we do next? Let's do it. The integral of dA is simply 4 pi r squared. If I now want to use Gauss's law, I make epsilon times this equal to Q enclosed. And look, how beautiful! 5 minutes before the day is over, we have gotten to something we did before, using a very convoluted Coulomb's law.
Huh. Cool.
So, that's how we got that. The electric field is K, Q enclosed over R squared. This is the electric field for a point charge. Now, life is going to be hard because I will ask you to find the electric field somewhere. Not out here, but perhaps somewhere here, but perhaps somewhere there. So let's see what the electric field is going to look like, okay? Well, obviously, in this case, because I don't have two concentric shells, which is coming like two concentric cylinders, so the electric field inside is 0 because you can see from this Gaussian surface, there is absolutely no charge enclosed in this Gaussian surface. So this is theorem 1, and this is theorem 2. Yeah?
Yep.
And because